Hello. Yeah. So, hello everyone. So today we will talk about assignment for week 4 for the course Classical Mechanics of a Single Particle. And the course instructor is Professor Shubhati Banerjee and I am the PMR of NPTEL. So let's start for today. So here basically we will talk about some important questions based on this assignment for week 4 lectures, and these will be the previous year questions obviously. So okay, let's start. So this is the first question. According to Bertrand's theorem, for f r proportional to 1 by r square and f r proportional to r, which of the following is true? Okay, so basically to know the answer of these questions we have to little bit recapitulate whatever it was there in the lecture series. So lecture series told us that what is the Bertrand theorem. Okay, so this one we have to figure it first. So I am going to write here, maybe here, yes. So what I want to tell here, that what is the Bertrand's theorem, then we can understand what the question means and what is the answer for this question. So theorem. So this is nothing but it is applicable for the central force field, but obviously not all the central force field. Only two types of central force field will be in this category. Right? So the theorem what sir was mentioning in his lecture, it was like only for two. I am focusing here two, right? Two central force laws every bounded. I just want to focus here this one as well, bounded motion assertively and then associates a closed trajectory. Okay. So the thing is that here two things we have to mention. Bertrand's theorem told us that it will be applicable for central force, that is the first one. So note, if I just tell, it is applicable for central force laws. It is applicable only for two central forces. And what are the two? One is inverse square law and another one is harmonic oscillator. And the third one is very much important, that the orbit should be bounded. Okay, so bounded means what? Bounded means, I can tell you one more important point here, that the point word is bounded means our total energy is less than 0. Unbounded means our total energy is greater than 0. For these two, it may be I can see these two from inverse square law as well. Inverse square law force. From these two, I can see that bounded means, okay, unbounded means it can be scattering as well. Okay, so this is the case. Now come to the question. So what is the Bertrand's theorem told us? It tells us that only for two central force laws, two central force means what are the two central forces? One is inverse scalar law and another one is the harmonic oscillator. So for these two types of central forces, every bounded motion, if the motion is bounded, then it will assert a closed trajectory. Okay, so that means applicable for central force laws and specifically two laws. One is inverse scalar law and another one is harmonic oscillator. And the orbit should be bounded so that we can have the Bertrand's theorem, which told us that the trajectory will be closed. Now come to the question here. According to Bertrand's theorem, for Fr, you can see here this is nothing but inverse square law, and this is nothing but harmonic oscillator. Which of the following is true? So which of the following is true? All the motion will be bounded. That is not correct, because all the motion cannot be bounded. If the energy is less than 0, then only it will be bounded. For unbounded case, E greater than 0, and this is for this one. So this one is not correct. Always. The total mechanical energy is always negative. That is also not correct, because we can see for the inverse scalar law itself, we are having some portion where the energy is greater than 0, that means positive. All bounded motion will have the closed trajectory. That is true. All bounded motions will have closed trajectory. That means it is already said that the motions are already bounded. Now we told that if the motion is bounded, then the trajectory should be closed. The trajectory is closed only when total energy vanishes. That is also not correct. So I can give you one picture here. Oh, sorry. That's better. It was given in a SAS lecture as well. You can see if V effective versus R we are plotting for inverse scalar law, the plot is looking like that. Like that, okay? I mean, it should be smooth. I am not making it that much smooth. So if I draw a line of this, then you can see that this one is one energy. This one is another energy. This one is another energy. So for E1, I have a minimum point, only one point is there. But for E2 I am having 2 points, 2 R minimum and R maximum, and this is like a bounded condition. So E2 will give bounded motion. E1 will also give the bounded motion only with the 1 point of R. But E3 is giving unbounded motion. Why it is like that? Because you can see that for E3 we are having only 1 point as R minimum, but there is no R maximum, where it is cutting. Like the turning point is, we are having only one turning point for E3, but for E2 we are having 2 turning points. So that means E2 and E1 is giving the bounded motion, but E3 is giving the unbounded motion. Now from this plot we can see that E3 is greater than 0, where E1, E2 are less than 0. That means the energy which have the value less than 0, these are giving the bounded motion. The energy which has the value of greater than 0, that is giving unbounded motion, right? So that's why, so all the motion will be bounded. No, it is not correct. When E greater than 0, then it is unbounded. So that is not correct. The total mechanical energy is always negative. That is also not correct, because you can see that sometimes E is greater than 0 also. All bounded motions will have closed trajectory. That is the actual statement of the Bertrand's theorem. All the trajectory is closed only when total energy vanishes. No, that is also not correct, because you can see total energy vanishes means that means this point energy is 0. But we can have a less negative energy. In that negative energy condition also we can have the bounded motion, because bounded motion is there, that's why we are having the closed trajectory. So the trajectory is closed only when the energy vanishes. That is also not correct. Okay. Now coming to the second question. So for motions under an attractive inverse square force field, what is the angle between angular momentum and the Laplace range vector? So first of all, what is Laplace range vector, so that we can understand that what will be the answer for this question. So let me write here. Range vector. So sir was telling these things clearly, that this is denoted as A. Now what is A here, and then we will find what will be the answer for this question. So A, right? It is basically, let me write here, A. It is only conserved in inverse square law force. Okay. So and A is that Laplace range vector. Okay, so what is the expression for that A? A has the expression as P vector cross L. P is the linear momentum, L is the angular momentum, minus M K R cap. Why K? Because you can understand K, how K is coming. F of R is like minus K by R square R cap. So from there our K is coming. I can write it like F R cap as well. Okay. So this is conserved only in the inverse square law. Now coming to the question. For motions under an attractive inverse square force field, as it is already mentioned that this is an attractive inverse square force field, that means our A is conserved. Okay. What is the angle between angular momentum and the Laplace range vector? So it means that what is the angle, that is A dot L. A dot L we have to calculate. Okay. So let me write here. Or L dot A. It is exactly same, because we can understand that these two are exactly same. So what is the expression for that? A dot L. This is simply vector calculation, vector algebra. So we will quickly write the A vector as P cross L minus M K R cap dot L vector. So first we will do this one minus M K R vector L vector. Now let's say I am writing here this one first, this one second. So first one is P cross L dot L. So you can write, okay, to have the answer I can just tell you one thing. A dot B cross C equals to B dot C cross A equals to C dot A cross B. So this is correct for the vector notation. Now you can see I can write it like L vector dot B plus A, because dot product can come. So okay, so from there I can also write, you can see here it can be written as A, this is B and this is C. So I can write this one this one equals to this one, so that means B dot C cross A is also fine. So B dot or C is L cross L. Now you can understand any vector cross and the same vector will always give a 0 answer, because the angle between these two are giving the 0. So that means, okay, I can just write it here. This is mod R, then mod R, then sine 0. So obviously it will give a 0 value. So if I calculate for this one case, P vector plus L vector dot L vector equals to P vector dot L vector or L vector. So it is giving us 0. Okay, so the first one is giving me the 0 answer. Now the second one. The second one is having the expression, where is that? Okay, mk r vector dot L vector. So if I will write this one, let's say I am writing this one k, so L I can write it r cross p, angular momentum. So r cross p I can write also like r cap cross m v. So this is r cap cross m r dot r cap plus r theta dot theta cap. So this is this one plus r cap cross m r theta dot theta cap. Okay, and I can write it as a bracket. So I can write again mk. Okay, m I can just take it outside, then r cap dot I can also okay dot r cap cross r dot r cap plus mk r dot r cap cross okay, that will be m square r theta dot theta cap. So m square k r cap dot r cap r dot r cap plus m square k r cap r cap plus r theta dot theta cap. Now you can see the first one. Let me write here, this is A and this is B. So A is giving me m square k r cap dot r cap plus r dot r cap. So this is giving me m square k r dot r cap dot r cap plus r cap, and r cap plus r cap is obviously giving 0 value. So this is 0. Now coming to the B. B is m square k r cap dot r cap okay, this is cross, not cross, this is cross r cap r cap cross r theta dot theta cap. So r cap cross r theta dot theta cap. Is it fine? Yes. So now you can see r square theta dot r cap cross theta cap. Okay. Similarly, again I just want to use this expression. C plus A C dot A cross B. So if I will use this one here, then it will be n square k r square theta dot, now A dot B cross C. So I can write here C dot A cross B, that means theta cap dot r cap cross r cap. So r cap cross r cap again gives me 0. So now you can see that B is 0, A is 0. So if that was A plus B, as a whole it is 0. So that means our 2 is also 0 and 1 is also 0. So we had 1 and 2. So A dot L, both are giving me A dot L 1 plus 2. So that is minus. So it is also giving 0, it is also giving 0. So as a whole I have the answer 0. So that means cos theta equals to A dot L, which is 0. So cos theta equals to 0 because mod A not equals to r. 0 and mod L not equals to 0. So theta equals to 90. Okay. So from here we can get the answer that the angle between for motions under non-attractive inverse square force law, what is the angle between angular momentum and the Laplace transfer range vector? This is 90 because A dot L is giving 0, which is this, and theta equals to 90. Okay. So now come to the next question. Which of the following is true about Kepler's second law? Okay, so what is Kepler's second law? That we need to know at the very first. Okay. So Kepler's second law, if I just write here, it says that radius vector of a planet sweeps out equal amount of area in the equal time. So what does this mean? Radius vector of a planet sweeps out equal amount of area in the equal time, which means if I have a motion, like I just have a motion like that, let's say, so let me draw here. Good. So in the first Kepler's law, it was saying that the planets are moving in the elliptic orbit. So elliptic orbit, and one of the forces will be the sun. So it's similar, like let's say I am having one sun here, and yes, this one. At the first, let's say I am having here and I am having here. So the distance between these two, let's say dr. So this is r1, it is r2. So r2 is nothing but r1 plus dr. So Kepler's second law told that the radius vector of a planet sweeps out equal amount of area in the equal time. That means dA, A is the area vector, dt is equals to 0, and A is constant with respect to time. Yes. So this is the second law. Okay, which of the following is true about Kepler's only valid only for elliptical planetary motion? No, this is not correct. It is applicable for all the central force motions. Applies only to circular motion, that is also not correct. Applies to all motions under central forces, that is correct. Does not apply for non-conservative forces, that is also not correct. So it is applies to all motions under central forces. Why? Because I will just explain that one in the later questions as well. So for right now for the time being, we will just see if this expression we have to satisfy. We just need to conserve angular momentum of the system, and for central force problem, irrespective, it is very important, irrespective of any conic section, we have L as concept, right? We have already seen that one. So to conserve angular momentum, we need to have the concept angular momentum, and for the any type of central force problem, we have the L as concept. So that means we just need to be a central force motion. This is needed for having the Kepler's second. So this is the question's answer. So this is the third question's answer, right? So to have the Kepler's second law, we just need to conserve angular momentum, and for any type of central force problem, we have the conservation of angular momentum. So that's why it is applicable to all the central force problems. Okay. A turning point in a one-dimensional motion under a central force signifies what? Let me first write here what is turning point. To know what is turning point, first of all we need to write the total mechanical energy. This is total mechanical energy, which is effective kinetic energy plus effective potential energy. In simple language, I can tell that total mechanical energy is nothing but true kinetic energy plus through potential energy. Now if I just going to write for central force law, we have half m r dot square plus h square by 2m r square plus p at r equals to f at r. Okay, so not f at r, it will be energy, total energy. So this is the for the central force law, this is the total mechanical energy. So now you can see here our total energy is coming as this, and this whole is telling us effective potential energy, and this is effective kinetic energy. Okay, so this is effective potential energy, this is effective kinetic energy. Now what is turning point? Turning point means the point where V effective is equal to E. Now you can understand at turning point V effective equals to E. That means our E had effective kinetic energy plus V effective, right? So at turning point effective kinetic energy is 0. Why? As energy is equals to V effective. Okay. And what is effective kinetic energy? This is half m r dot square, which is 0. So that means I can write m not equals to 0. So r dot square is 0, which is r dot is equals to 0. So at turning point we are having r dot equals to 0. And what is r dot here? Okay, so this is r dot equals to 0. And what is r dot? R dot means radial velocity. So you can see that 0 speed, it is not correct, 0 acceleration not correct, 0 radial velocity, 0 angular velocity is also not there. Angular velocity is like VA theta, like r theta dot, that is not 0. So radial velocity is 0. So the third option is correct. Okay. So now coming to the fifth one. For a repulsive inverse square law, first of all, repulsive inverse square law, that means Fr is proportional to K by R square. Or here it is a repulsive, attractive repulsive means like there will be a plus. Which of the following is or are true? Okay. The trajectories are conic sections. Yes, that is correct. All motions are bounded. No. Mechanical energy is always negative. No. The trajectory is always circular. No. Why it is not correct? Because you can see that for any inverse square law, or basically I can say like that for any okay, the value of r will be p by 1 plus e cos theta. The derivation was already given by sir, so I am not going to derive all the calculations of this expression, but we can see here that our p is like semi latus rectum and e is like eccentricity. Eccentricity. So this is nothing but that r equals to p by 1 plus e cos theta. This is nothing but a conic equation. Why we are telling it as conic equation? That means like depending on the value of e, we can have ellipse, circle, parabola or hyperbola. Okay, so that's why we are writing here r equals to p by 1 plus e cos theta, that is a conic equation. So now coming to the options, the trajectories are conic sections, that is fine because I can write it like this one. Now all motions are bounded, obviously not. If I see the plot here again, so this one will not give the bounded one. Mechanical energy always not negative, that is not correct because here you can see that the mechanical energy is positive. The trajectory is always circular. No, it is also not correct because it can be 4 types. Like one is circular. Circular is just a type. Okay, it's not in general case. Elliptic, parabolic or hyperbolic. So these 4 options are possible here. Okay. Okay, so for this case, what is the correct answer? Trajectories or conic sections. That is correct. Okay, now coming to the next question. Yes. So today we will have basically I think 20 questions. And yeah, and right now it is. The particle moves in a circular orbit under a central force field. So you can see that the force field is attractive inverse square law. because it is a minus sign here, and 1 by r square is there, so attractive inverse square power. What is the correct expression for the centrifugal potential at r equals to r0? So basically, what is centrifugal potential? If I just write the energy conservation equation, half m x dot square plus l square by 2 m r square plus pr equals to E. So this is nothing but centrifugal potential. So they are asking that what is the correct expression for the centrifugal potential at r equals to r0. So at r equals to r0, centrifugal potential is L square by 2m r0 square. Simple. Just we have to replace r by r0. So this is this one. This one is not correct. This one is not correct. This one is not correct. L square by 2m r square at r equals to r0. L square by 2m r0 square. Okay. For a particle in elliptical orbit. Okay. For a particle in an elliptical orbit under central force field, total mechanical energy is constant. What is the length of the major axis of the Earth? So obviously, total mechanical energy is constant. That should be energy is constant. And what is given here? Central force field find, and it is an elliptic orbit. Okay. So elliptic orbit means elliptic orbit means we have 0, E1. Eccentricity will be in between 0 and 1. Okay. Now from the conic section, I can see that P by r equals to P by 1 plus E cos theta. So sir was also explaining that one, but still as the question is coming, so I am also going to explain this one. Okay. So here we can see r plus r e cos theta equals to P. Okay. Now r can be written as x cos theta. Actually I can write it like that. X equals to r cos theta, y equals to r sin theta. So y square plus x square root, that is given as r, right? So I am going to put this expression here, root over x square plus y square plus r cos theta e. Now we can see x square plus y square plus r cos theta is nothing but x e is equals to p. Okay. So whatever x square plus y square can be written as p minus x e, and then x square plus y square will give p minus x e whole square, which is p square minus 2pxe plus x square is square. Right? Okay. So p square minus 2pxe plus x square is square. I can do one thing here. X square 1 minus square plus y square my plus 2pxe equals to p square. This one I can do. Yes? Okay. So now for ellipse, 0 less than e less than 1. That means whatever the value will be there, e square is smaller than 1. Okay. So I can write one thing here. So that means 1 minus e square is a greater than 1. Positive value. Okay. So I had x square plus x square plus 2px divided by 1 minus e square plus y square by 1 minus e square is equals to e square by 1 minus e square. Okay. Now what I will do, I will just do a little bit trick here, as I was also discussing in his lecture. I'm just going to add one term here, e square is square by 1 minus e square and whole square. So if I will add the left hand side, I have to add that one in right hand side as well. Okay. So now I can have the expression x plus pe by 1 minus square whole square plus y square by 1 minus square equals to 1 minus square whole square square minus square plus p square square. So it is like p square by 1 minus square and whole square. Now you can see here that x plus pe by 1 minus square whole square divided by p square by 1 minus square whole square plus y square by 1 minus square divided by p square by 1 minus square whole square equals to 1. So it can be compared as x square by a square plus y square by b square equals to 1. So where a square is nothing but, you can see here, this whole is x square by a square. A square is p square by 1 minus square and whole square. So what is a here? A is p by 1 minus square. Okay. Now what is p? P you can calculate from the previous calculations, whatever I was telling there. So that is nothing but h square by mk, and also e square equals to 1 minus 2 mod e l square by mk square. Why I am taking mod e? Because I have the magnitude, I just need the magnitude, but actually e is a negative one, right? Because we are talking about the bounded case. So 1 minus square will give me 2 mod e l square by m k square. Now a will be what? A is what? L square by mk into 1 by 2 mod e l square by m square. Okay, so it is l square by mk square by 2 mod e l square. So it is l square will cancel out, a will cancel out, k cancel out, k by 2 mod e. So I will have semi-major axis A as k by 2 mod e. But in question they are asking major axis. This is 2a, which is k by mod e. So how to know what is semi-major and what is semi-minor axis? This. Okay. So here, so this one is A, this whole one is 2A. Now similarly, this one is B, but I will, if I take 2b, that means this whole is 2b. Okay. Yeah, so this is 2b. So this is the case. So now in the question, you can see the question here. What is the length of the major axis? So we have A equals to K by 2E. Now major axis is 2A, which is K by E. So this one is correct. This one is not correct. It is not correct. It is not correct. So this one is correct. So for that, what we did, we just did the elliptic orbit and then R equals to cos theta. Then for ellipse, we calculated the value and we got that A will be this x square by a square plus y square by b square equals to 1. That is the general solution for ellipse. And then A is like b square by 1 minus b by 1 minus e square. So now we are just taking the values of b and we are getting the answer. Okay. Now come to the 8th question. Under the same inverse square field for circular and parabolic orbits with the same angular momentum, what is the relation between the minimum radius of parabolic orbit and radius of circular orbit RC? Okay. So first of all, parabola means it is coming out from e greater than 0, but is unbounded system. So unbounded system means parabola will have only R minimum is finite, but R max is infinite. Okay. So, okay, now come to the question. Under the same inverse scale law, like if R, let's say, proportional to something k by r square. So this is the inverse scale law for the circular and parabolic orbits with the same angular momentum. That means our L for parabolic is equals to L for circular. What is the relation between the minimum radius of parabolic orbit RP and the radius of circular orbit RC? Okay. To get, okay, let's say if R is given as minus k by r square. Okay. So now, if I take our v of r, which is minus integration fr dot dr, so it is minus k by r square dr. So it is k by r square dr, which is minus k by r. Okay. So our VR is minus k by r. So now quickly I can write it: half m r dot square plus L square by 2m r square minus k by r equals to e. And what is V effective here? V effective is L square by 2m r square minus k by r. Now for the circular motion, this is representing the circular motion. So what does this mean? This means that V effective derivative with respect to r is giving me 0, because this is the minimum point for this curve. So if I do the derivative, so that means dtr of V effective is giving me minus 2L square by 2m r cube plus k by r square. So minus L square by m r cube plus k by r square equals to 0. Now you can understand clearly that at r equals to rc, L square by m rc cube equals to k by rc square. Actually this is r cube. Okay, so now you can understand L square by M RC equals to K. From here RC is L square by M K. Okay, so this is the expression for RC. Now coming to RP. What is RP here? So this is the circular radius. Radius of the circular orbit. Now coming to the RP. For parabola, we have E equals to 1. Now you can see that okay, so V effective equals to L square by 2 M R square plus okay, so V effective was L square by 2 M R square plus VFR, right? And here so as E equals to 1, that means E square will also be 1, and then we have the E square expression as 1 minus 2 mod E L square by M S square. So you can see that if I will write here E square equals to 1, that means this. So our mod E will be 0. If mod E is 0, that means I will have half M R dot square plus V effective is 0. Right? And what is the conic section for this case? The conic equation was P by 1 plus E cos theta. And now E equals to 1. That means I will have R equals to P by 1 plus cos theta. Now for parabola, to get mean of R, what we can do? R mean means it should be the denominator should be the maximum one. So the maximum value of denominator is 1 plus cos theta value maximum is 1. So it is like P by 2. And what about R max? R max is P by 1 minus 1, which is infinite. So as I already told that for parabola, I think it is already given here that yes, for parabola coming out from E greater than 0 and more system, so R is finite but R maximum is infinite. So it is also coming from that equation as well, that R equals to P by 1 plus cos theta and E is 1. So R max is giving us infinity, but R minima is giving us P by 2. So this is nothing but RP in that question. So this is P by 2. So now what is P here? P is M. P is our L square M by K. So our P will be M L square by 2K. And what was RC? RC we calculated and it is coming as L square by MK. No, just a minute. P expression is what? P expression is L square by MK. Yes. P expression is L square by MK. So it is L square by 2MK. Now you can see here RC was L square by MK and RP is L square by 2MK. So I can see that RC is 2 into RP, or otherwise I can write here RP equals to RC by 2. So this one is the expression RP equals to RC by 2. So RP equals to RC by 2. This one is not correct. So for that case, what we have calculated, we just calculated for the circular orbit case that if I have the circular orbit case, then V effective dV effective dr equals to 0 because this is the minimum point. So if the derivative is 0, then from there at r equals to RC, we can get the expression of RC. And for parabola, we are having equals to 1, so e square equals to 1 minus 2 d square by nt square. So if I put 1, that means e equals to 0. So if e equals to 0 means half a matter square plus v effective equals to 0. Otherwise, we can say that the current equation is r equals to p by 1 plus e cos theta. If e equals to 1, then it is simply r equals to p by 1 plus cos theta. And for parabola, to get minimum of r, we will have the denominator as maximum value. So the maximum value of cos theta is 1, so it will be p by 2. And for r max, we will get the minimum value of 1 plus cos theta, and minimum value of cos theta is minus 1, so 1 minus 1 will give the 0. So it is like p by 0 is infinite. So RP is p by 2 simply, which is our minimum in that case. So p is s square by nk, so RP will be s square by 2 nk. And RC is s square by nk, we have already got that one. So RP is s square by 2 nk, so RP equals to RC by 2. Okay. Now coming to the 9th question. A particle moves in an ellipse with semi-minor axis P and period T. If it moves in another ellipse with semi-minor axis to B, what will be the new period? Okay, to get the answer, we just need to do one thing. In that lecture, I was talking that from the Kepler's third law, we will have a square balances A cube. And what is A? Just means, remember here, A is semi-major axis. But here, what they have told that T is proportional to, let's say T to the power alpha is proportional to B to the power beta. So we have to calculate that alpha and beta value so that we can answer the question. So, to have the answer of this question, we just need to calculate how our T is varies with B. So let's go back to that derivation. Basically, we have dA dt, which is constant from the second law, and also it is half r square theta dot. So it is like L by 2m, which is h by 2. So this is constant because h is constant. It's well. Okay. Now for, and what is A? A is nothing but L by 2m into T because dA dt is there. So for an ellipse, it is talking about ellipse. So A is nothing but pi AB, where A is semi-major axis and B is semi-minor axis. Okay. So I will write here pi AB equals to L by 2m into T. Okay. Now T can be written as 2m pi AB divided by L. Now what is A here? A is K by 2 mod E, and B is what? L by root over 2 EM. So if I just calculate these things, let's say I just need the dependency of T on B. So I have to represent A in respect of B. So now A square by 4 mod E square. Now B square is L square divided by 2 mod E M. Now let me write here 2 mod E. 2 mod E is L square by M B square. And A was what? A was K by 2 mod E. So I can write here K by L square into MB square. Okay, and what was T? T was here 2m pi AB divided by L. So I just put that value 2m pi, and A is nothing but kmb square by L square. So kmb square by L square into L and another B. Now you can see that our T can be represented by the time period capital T. So capital T is 2m pi k m square by L cube B cube, because here it is B square and here it is B. Now you can see all the functions, whatever it is there, k is constant, L is constant, m is constant. So T is proportional to B cube. So in that question what was we were talking that T to the power alpha proportional to B to the power beta. So here alpha is 1, beta is 3. Now we got the expression that T is proportional to B cube. Okay. If T is proportional to B cube, now come to the question again. A particle moves in an ellipse with semi-minor axis B at time period T. If it moves in another ellipse with semi-minor axis 2B, what will be the new period? Okay. Now my B is changing to 2B. So our T prime will be 2B whole cube. So it is like 8B cube. So and also T was B cube. So T prime is nothing but should equal 8T. Okay, T prime is 8T. So this one is calculation. So how we calculated? We just calculated that how T is going to be vary with B, and we found that T is proportional to B cube. So if 2B is there, then 2B to the power cube, that means 8B cube. So it is 8T. Okay. So coming to the second one, 10th one. So in the 10th one, in an attractive inverse square. Okay, first of all let me write here attractive inverse square. That means FR is minus K by R square. What type of orbit does a particle with zero total mechanical energy flow? E is 0. Just mention this. If E is 0, okay, so E is 0 means it will be, okay, I can tell you one thing. E square is 1 minus 2 square by K square, something like that, right? So if E is 0, that means you can see E square is 1. So E is equals to 1. So if E equals to 1, that means what type of Conic section is there? E equals to 1 represents parabola. So for parabola, we will have E equals to 0. So it is parabolic orbit. This is not a circular orbit, this is not a elliptic orbit, this is also not a spiral orbit. This will be a parabolic orbit. In an attractive inverse square field, what type of orbit does a particle with zero total mechanical energy flow? So this will be parabolic orbit. Okay. Yeah. So according to Bertrand's theorem, the following force law allows closed and bounded orbits. So this is very simple because we just at the very first of this today's lecture we talked about that what are the conditions for getting the Bertrand's theorem. And Bertrand's theorem says that if I have Fr proportional to 1 by R square or R, in this situation I will have the Bertrand's theorem. But you can see here these are given in terms of V. So quickly we will calculate VR. Here is nothing but Fr dr. So for having Bertrand spelling here DRAND. Bertrand's theorem, true, f of r should be, let's say, minus or plus k by r square, anything. So for that case, VR will be, this is one category, VR will be integration k by r square dr, which is nothing but k by r, or something which is proportional to 1 by r. And coming to the second one was what? If r proportional to r, which is harmonic oscillator. Now let's say if r is k into r. So phi will be minus kr dr. So it is minus k r square by 2. So as a whole I can see Vr will be proportional to r square. So these two will give the Bertrand's theorem. One is V proportional to 1 by r and proportional to r square. So let me go to the option here. 1 by r and r square. So these two will give the Bertrand's theorem. This will not give, this will not give. And also it is given in the bracket as well, inverse scale law and harmonic oscillator potential. This is correct, this is correct. Okay. For a particle moving under an attractive inverse scale central force. Attractive inverse scale central force. That means Fr is again minus k by r square and central force. The angular momentum is conserved, so obviously it is correct because as it is an intercentral force, so always angular momentum will be constant. The Laplace-Lagrange vector is conserved. Yes, that is also correct because it is, I can write here, Laplace Lagrange vector is conserved in only in inverse square law force. Okay. So as it is saying that attractive inverse scale central force, that means the Laplace-Lagrange vector is constant. Okay, the orbit is a conic section, ellipse, parabola, hyperbola. That is also correct. Kinetic energy is conserved. Kinetic energy is conserved, that we can't say. Circular orbit as the only trajectory. No, that is also not correct. So these three are correct. That angular momentum is conserved. Laplace-Lagrange vector is conserved. Orbit is a conic section. Conic section means what? R equals to P by 1 plus E cos theta. That should be applicable for like inverse attractive inverse scale central force, and we have seen that one as well. Okay, so for this case these three options are correct: angular momentum, A, and conic sections. Okay. Now this one. What is that? Anything else? No, this is 13. Kepler's second law implies. Okay. Kepler's second law was there that dA dt equals to constant, and we calculated that one by A equals to h by 2. So this is constant. So that means equal areas are swept in equal times. Yes, this is exactly correct. That's why dA dt is constant. No, actually dA, yeah, dA dt, yes, dA dt is constant. Okay. So this one is, first one is correct. It is valid for all central force motions. This is also correct because we already told that for this calculation I just need to have the angular momentum conservation. Only this one I need. Maybe I can write the expression derivation of that. So for derivation, so I can see that half, it is like r plus dr dt. So it can be written as half r square dt of theta. So you can see that half r square theta dot, and we have h as r square theta dot, and h is constant if angular momentum is constant. So only we need the condition that dA dt equals to half r square theta dot will be h by 2, which is constant, given that angular momentum is conserved. So this is the only one condition to mention. It is valid for all central force motions. We can for all central force motion, angular momentum is conserved. It follows from conservation of angular momentum. Yes, that is also correct. T square equals to c a cube. Okay, that is not coming directly from the second law. Like second law is not implying that one. It is implying the third law. Only applicable for electric orbit. No, that is not correct. So equality has written equal times. That is correct. It is valid for all central force motions. That is correct. It follows from conservation of angular momentum. That is also correct. And the T square value is a cube. That is also correct. But it is for third law. It is not coming from the second law. And only applicable for electrical orbit. That is also not correct. It is applicable for all the cases, all the central force motions. Okay. Now at the turning point of a radial motion in a central force field, mark which one is or are correct. Okay, so turning point, as we have already told, at turning point, half m r square plus v effective equals to E, where v effective is L square by 2 m r square plus v. So at turning point sorry, v effective equals to E, so half m r dot square will be 0. That means r dot will be 0. This is the turning point expression. So radial velocity value vanishes. That means I told you that r dot equals to 0, so it is correct. Angular momentum remains constant. Yes, that is always constant. It is constant. Okay, so angular momentum is always constant. So because whether it is coming as 0 or not, so that is whether it is a turning point or not, as it is under the central force field, so it is obviously constant for all the time. The effective potential energy equals the total mechanical energy. Effective potential energy equals to the total. Yes, that is also correct. As I told, V effective is equals to E. So R dot equals to 0, that means effective potential energy equals to the total mechanical energy. All the these are correct here. So radial velocity vanishes, angular momentum remains constant, the effective potential energy equals the total mechanical energy. Okay. Now coming for the next question. For motion under a repulsive inverse square law, the motion under a repulsive inverse square law, that means if R is proportional to k by n square, trajectories are hyperbolic or parabolic conic sections, the total mechanical energy is positive, the orbit is unbounded. Okay, so first of all, just let me remind you that how we can calculate these things, and also in this conditions tell that what will be the plot for effective potential versus R. Okay, so let me write here. F of r is given by k by r square. As it is repulsive, that means k is greater than 0 and fr is also greater than 0 and there is a plus sign. So what will be here? V, right? So here our V will be minus fr dr. So k by r square dr. So it is like this is, there will be a minus sign, so it will be k by r, simply k by r. Okay, so if it is a k by r case, then we can understand that half m r dot square plus l square by 2m r square plus k by r equals to e. Now we just need to plot V effective versus R. Now what is V effective? V effective is L square by 2m R square plus K by R. Now we can understand this is coming as R cannot be minus 1, so we will just have this one. So it will be simply this. Okay. So the trajectories are hyperbolic, parabolic, conic sections. Yes, the trajectory can be hyperbolic, parabolic when at this position. Let's say our E is this one. So E is greater than 0, right? Because this is the 0. So our okay, so if it is a 0, but we can't have a bound state. Why? Because there is one point where we are having the turning point, but here in the right side there is no turning point. So for this case, only one turning point we are getting. So we can say that at E greater than 0, this will give me a parabola or hyperbola, conic section, because these are unbounded. Parabolic or hyperbolic conic sections. The total mechanical energy is positive. Yes, for this case, like parabolic and hyperbolic section, the total mechanical energy is positive. That is good. The orbit is unbounded. Yes, the orbit is also unbounded, because we can see that E greater than 0, that means there is no second turning point. Okay, so this is the orbit is unbounded. The effective potential for a particle of angular momentum L and an attractive inverse square force is, okay, prove this. The effective potential of a particle under the angular momentum under the inverse square force law. Inverse square force law. Okay. Proportional to inverse square force law. So f of r is equal to minus k by r square. I can write it like that. This. So quickly I can write what is the V of r. V of r will be minus f r dr minus k by r square dr. So it is k by r square dr. This will give me minus k by r. Now, I can write it here that plus c as well. But at r tends to infinity, Vr is 0. So 0 is r by infinity plus c. So that is 0 plus 6. So c is 0. That is fine. So Vr is k by r minus k by r. Now the equation is half m r dot square L square by 2m r square plus VR equals to E. And what is V effective? V effective is always L square by 2m r square plus V of R. Now here V of R is minus K by R, so I can write it 2m r square minus K by R. So this is V effective. Okay. L square by 2m r square minus K by R. Fine. It is a stable minimum corresponding to a circular orbit. Okay, let me see that one as well. Also draw the V effective versus R plot. So V effective versus R plot, sir has already calculated. So V effective is L square by 2m r square plus minus K by R. V effective, here it is R. You can see that this type of plots are there. So at this point I can see the potential is giving the minimum value. So let's say it is E. So at this point we will have the minimum potential. So how to get the minimum potential? Just simply V effective dr equals to 0. This point will give me R equals to R0, that will give me the minimum potential. And what was the question? It has also the stable minimum corresponding to a circle. Yes, we can see from the plot that it is a stable minimum. Or we can also do that one like that. Let's see, let me write here. dV effective dr is minus 2 L square by 2m r cube plus K by R square. So that is 0. So it is like K R equals to R0 equals to L square by M K. So this is giving our stable minimum. How stable minimum we can say? We just do the double derivative here, d2v effective dr2. It will give me 3L by m r to the power 4 minus 2k by r cube. Now if I put the value 3L by m r to the power 4, r is L by mk, L to the power 4 m for k4 minus 2k by L cube m cube k cube. So you can see here 3 m cube k4 divided by L cube minus 2 k m cube k4 divided by L cube. That is giving me greater than 0. So greater than 0 means if d2v effective dr2 greater than 0, r equals to r0, stable minimum. That's what is given in this question as well. So this is also correct. Okay. Now come here for an elliptic orbit of semi-major axis A. Elliptic orbit of semi-major axis. Okay. So they are telling that we have to prove the total mechanical energy is E equals to minus k by 2a, and orbit is bounded, major axis at this 2a. Okay. For elliptical orbit, this one is correct. Okay. Now we can write where r equals to 2 by 1 plus e cos theta. Again the same calculation is there, so that we can we have already calculated, so we just got the answer that A equals to P by 1 minus E square, and P equals to semi latus rectangle. It has the value in L square by mk. So, and also E square equals to 1 minus 2E L square by mk square. So A will be L square by mk divided by 2E L square into mk square. So you can see that I will just have k by 2E. But as the conic section is elliptic, means our E is less than 0. That means the bounded system is there. So I can have A is k by 2E, but our E will be minus k by 2A. Okay? As E is bounded, so E will be negative value. So the first one is term. The output is bounded, obviously the output is bounded, otherwise it will not be the term. So you can see that this one is also there, this type of this, and the energy is like that. So here our maximum is there, so it is like bounded one. The major axis is 2A, yes, because the same major axis is A, so the major axis length is 2A. So it is k by what? Okay. Now coming to the next question. For a particle in a circular orbit under an inverse scale law, two of these things, the centrifugal force balances the attractive central force. Okay, you have to clearly see that this is a circular orbit. Circular orbit means obviously equals to 0 first of all. And centrifugal force balances the attractive central force. Okay. E square equals to 1 minus 2E L square by m k square. So E equals to 0, right? And one thing is that the centrifugal force. What is centrifugal force? Is L square by 2m r square. Okay? And L square by 2m r square plus V of r is V effective. So for circular motion, dV effective dr equals to 0. Okay? So L square by m r cube equals to k by r square. So r is L square by m k. Okay. So that is centrifugal force. Centrifugal force means L square by 2m r square, and attractive central force. This is k by r. Centrifugal force. Actually, centrifugal force means that which is coming from. Let me write here this. Centrifugal potential is L square by 2m r square. So V sen is L square by 2m r square. Now you can see here F sen is minus dv dr. So it is like minus 2l square by 2m r cube. Okay, so it is minus l square by m r cube. Now central force, what was that? Attractive central force. So attractive central potential was minus k by r. So attractive central force F attractive, V attractive. So it is minus dv dr, that is minus del r of minus k by r. So it is minus k by r square. Now you can see here that was h square by m r cube. H square by m r cube is equals to exactly k by r square in circular case. Here it is minus, here it is minus. So how it is coming? Because you can see that this one. For circle, m h square by m r cube equals to k by r square. So if I take the minus sign both sides, then it will be minus minus. So minus h square by m r cube equals to minus k by r square. Minus h square by m r cube equals to minus k by r square. So that is coming exactly from the circular motion. So it was exactly same thing, but the question was a little bit tricky. They were saying that the centrifugal force, so centrifugal potential we know, so from potential we will get the centrifugal force, and attractive central potential we know, from there we will have the attractive central potential force. So these two are balancing, that's the thing. Obviously it was there for circular orbit and we have to prove that one. Okay, done. Now doubling the angular momentum increases the orbital radius by a factor of 4. Okay, angular momentum doubling. Okay, so our angular momentum was r cross p. So which is nothing but m r then p. Like, okay, we can write here explicitly. R cap cross r dot r cap plus r theta dot theta cap. So it is m r cap plus r cap will be cancelled out. So r square theta dot theta cap. Now we can understand a is m r square theta dot. Actually this will be r cap cross theta cap. So the mod if I take, so this should be m r square theta dot. So now I can have that L is proportional to r square. So if our r is going to 2r, then our L is going to 2r whole square, which is 4r square. That means 4 times our L. So the next question was also find that doubling the angular momentum increases the orbital radius by a factor. No, actually it will be doubling the orbital radius increases the angular momentum by a factor of 4. The total mechanical energy is negative. Yes, the total mechanical energy is negative because here our E is 0. So E square was 1 minus 2 mod E square by m k square. Now you can see that if it is 0, mod E is taking. So if I am not taking the mod E value, then it will come as plus E. So if it is 0, so obviously E is giving us minus m k square by 2l square. So that means E is negative. Square by m k square is minus 1. Yes. So E is negative. That is also fine. And also from that plot as well, we can understand that if I have the plot, so this one is the circular case. So here obviously the E is negative. This is the 0 value. So E is negative. Okay. Now we have another question on the panel. We will have the another one. Okay. By Kepler's third law, the square of the period t square is equal to a cube, where E is the same as x. That one we have already proved in that SAS lecture, but still we can do that one here as well. So for this case, dA dt is h by 2, which is half r square theta dot l by 2m. Okay. And for A is, so that means what? Like A can be written as L t by 2m. Okay, so now for ellipse, I can say A is pi AB. Okay, A is semi-major axis, B is semi-minor axis. Okay, so pi AB is L t by 2m. T is 2m pi AB divided by L. Now we have L equals to k by 2e and B equals to L by root over 2em. So B square is L square by 2em. So 2e is L square by m B square. Now I can write here A as, not A, I can write B. So A was k by 2e. So 2 mod e equals to k by a. Now we can see here, this is k by a equals to L square by m B square. So B square equals to A L square by m k. Okay. So again I can write here A to the power half L square, not L square, L mk to the power half. Now our t was 2m pi ab by L, 2m pi, a is a, b is root a, L by root over mk divided by L. So L will cancel out. Then you can see this will be 2 root m pi a to the power 3 by 2 by root k. And all other terms are constant. So t proportional to a to the power 3 by 2. So t square proportional to a cube. This one is correct. Now if a increases by a factor of 3, the period increases by a factor of 3 to the power 3 by 2. Let me see here. If a is going to 3a, then our t prime square is going to 3a cube. So 3a cube. Now our t prime will be 3 to the power 3 by 2 a to the power 3 by 2. So t prime will be 3 to the power 3 by 2 into t. That's what is mentioning here as well. If a is increases by a factor of 3, the period increases by a factor of 3 to the power 3 by 2. Yes, 3 to the power 3 by 2. Okay. So t prime is proportional to 3 to the power 3 by 2 into t. Now the last question. For motion in an attractive inverse square field. Okay, if this one the orbit is elliptical, if this one the orbit is parabolic, if this one the orbit is hyperbolic. So this is similar as whatever Sir was doing in his lectures. So what we will do here, we will simply take the expression and then we will calculate. Okay. Okay. Here. So the conic section was this. So which conditions? Elliptic, parabolic and hyperbolic. Okay. So 3 conditions we need to check. Elliptic, parabolic and hyperbolic. Elliptic. It will be elliptic if 0, E1. That we have to prove. Okay. So in this case, whatever it was there, so if I take x square 1 minus e square plus 2pex plus y square equals to p square. Now if e has the value 0 less than e less than 1, so e square is greater like positive. Okay, I can't say greater than 1 but positive. So 1 minus e square is also positive. Okay, so now we have x square, like after this calculation we did the calculation right before some time, so it will be like x. Okay, so for the motion in attractive inverse square field, they are telling that we have to prove these points. So previously we just had the conic section as r equals to p by 1 plus e cos theta. Okay, so we were representing that one as r plus r e cos theta equals to p. So it was like x square plus y square plus x e equals to p. So root over x square plus y square will be p minus x e. Then x square plus y square is p square plus x square is square minus 2pxe. Okay, so if I do that, x square equals to into 1 minus e square plus y square equals to minus 2pxe plus p square. So we will take this one as x square 1 minus e square plus 2pxe plus y square equals to p square. Now x square into 1 minus p square plus 2pxe plus y square, or we can do one thing, we will just divide all the things by 1 minus p square. So 2pxe 1 minus e square plus y square 1 minus e square equals to p square by 1 minus e square. So it will be simply x square plus 2pxe by 1 minus e square plus y square by 1 minus e square plus, let's say I am taking p square e square by 1 minus e square whole square. So it will be simply p square by 1 minus e square whole square. So the answer is like x plus pe by 1 minus e square whole square divided by e square plus y square by 1 minus e square by p square by 1 minus e square whole square is equals to 1. So like, okay, and here what is a? A is p by 1 minus e square. At which condition? When e is 0 and 1 in between the value. So that's why 1 minus e square is positive. So now we can see that I can write x plus pe by 1 minus e square whole square divided by a square plus y square by b square equals to 1, where a is p by 1 minus a square and b is p by root over 1 minus a square. So this one will give me an equation of ellipse. So whatever the first question was there, if e is 0 and 1 in between the value, then orbit is elliptical. That is fine. Now what is parabolic? E equals to 1. If e equals to 1, square is also 1, right? So if e equals to 1, then square is also 1. Now what were that calculation? It was like x square 1 minus e square plus y square plus 2pex equals to p square. That is the in general equation for every p. So if e square equals to 1, then you can see that x square coefficient will be 0. So y square plus 2px equals to p square. Right? Yes. X square equals to, so it is y square equals to p square minus 2px, which is minus 2p into x minus p by 2. This is the equation for parabola. Now come here, the third one. E greater than 1. If e greater than 1, then x square 1 minus e square plus 2pex plus y square equals to p square. 1 minus e square will be less than 0. So it will be minus x square into 1 minus e square plus 2pex plus y square equals to p square. So the similar equation will be there, but here will be x square 1 minus e square minus 2pex minus y square equals to minus p square. So x square divided by a square minus y square by b square equals to 1. And this is the equation for hyperbola. So you can see that one. So here basically we will have the same theme. The same thing is a equals to like p by 1 minus e square, but here so here basically as it is minus, so 1 minus e square is negative. So if I take e square minus 1, so I can write here e square minus 1, this will be positive. So now I am taking here e square minus 1, and again this one as e square minus 1, and b is exactly the same form like p by root over e square minus 1. So similarly as the ellipse, the hyperbola equation is there, but 1 minus sign is here because of that e square minus 1 calculation. 1 minus e square calculation. So this is the case. Okay. So here in this class we are talking about 20 questions. So this one is okay. This one is done. This one is also done. For a motion in an attractive inverse square field, this we proved this. Then this is the Kepler's third law of this. Then for a particle in circular orbit, doubling the orbital radius increases the angular momentum by a factor of L, A4. The mechanical energy is negative. This is the elliptical orbit of a major axis A. Major axis is 2A. Effective potential for a particle of angular momentum L under an attractive inverse square force is given this one. V effective equals to L square by 2m r square minus k by r. It has stable minimum corresponding to a circular orbit, and also draw the V effective versus r plot. This one is the trajectory hyperbolic, parabolic, positive and unbounded. Turning point of a motion in a circular force field. Radial velocity vanishes, angular momentum remains constant. The effective potential energy equals the total mechanical energy. Then Kepler's second law implies what? Then for a moving part of the attractive square central force, which one is concept? Ionia-Pantlen's theorem, the following force laws allow closed or boundary orbits. Which one is correct? The attractive inverse scalar, what type of orbit does a particle with zero mechanical energy flows? It is parabolic unit orbit. Then this is the case T to T, and it is 8. So this is the case for RP and RC relation. RP equals to RC by 2. Yes. And this is the case K by E proof. The square by 2m R0 square. Trajectory conic sections. Zero radial velocity. Applies to all motions under central forces. 90 degree. Barton's theorem, all bounded motions will have closed trajectories. That's it. Okay, bye.